Hello and welcome back, everyone. In this video, we will be exploring an advanced technique known as transfer learning. We will see what it is, its significance, and explore some popular architectures that can be used for transfer learning in the image classification space. So, let's begin. First, what exactly is transfer learning? In the context of deep learning, transfer learning involves taking a model that has been trained on a large generic dataset and fine-tuning it to adapt to more specialized tasks. This method leverages the learned features from the existing model, often related to recognizing shapes or textures, and transitions those features to make accurate predictions about new, specific sets of data. For instance, a computer vision model, in its initial layers, learns basic features like edges and corners, with the middle and final layers learning more and more sophisticated features depending upon the dataset used. For example, for an animal dataset, final layers would learn features like eyes, nose, tail, beak, wings, etc. And so, if we wanted to build a model for detecting different flowers like rose, tulip, orchids, and daffodils with transfer learning, we could take a pre-trained model built on general, everyday objects, keep its initial layers intact, and train only the final layers on our specific use case dataset. This would enormously save time and money and generate a better model if done correctly. These models also usually require smaller sets of specific data to generate good performance and are thus ideal for medical imaging use cases where the dataset is usually limited. Let's now look at some popular architectures that are often used in transfer learning for image classification tasks, starting with VGG16 and VGG19. Developed by the Visual Graphics Group at Oxford, these models are characterized by their deep architectures with 16 and 19 weight layers, respectively. VGG models use very small convolution filters, which allows them to capture minute details in the images. They are exceptionally good for image recognition tasks due to this depth and complexity, but are quite large in size, making them computationally expensive. Next, let's talk about the Inception and ResNet families. The Inception models, including Inception v3 and Inception ResNet, have improved computational efficiency and model accuracy through dimensionality reduction methods and sparse connectivity. This efficiency removed computational constraints and allowed the architecture to go deeper and wider without significant performance penalty. Later, ResNets, or residual networks, introduced a revolutionary skip connection feature that allowed training of significantly deeper networks by enabling feature reuse. Inception models have high accuracy and use computing resources efficiently, but have a slightly complex configuration. ResNet architecture, while enabling deeper networks without loss of performance due to skip connections, are still relatively large and computationally expensive. Moving on to MobileNet and EfficientNet, these are lighter architectures designed specifically for mobile phones and edge devices. MobileNet uses depth-wise separable convolutions that significantly reduce the model size and complexity. EfficientNet, meanwhile, scales up in a more balanced way using a compound coefficient which adjusts the depth, width, and resolution of the network systematically. MobileNet's use of depth-wise separable convolutions significantly reduces the number of parameters, making them lightweight and computationally efficient without sacrificing too much performance. EfficientNet's balanced and systematic scaling results in superior efficiency and accuracy at various scales. And that is all for this quick summary on transfer learning and some popular image classification architectures. We will add research papers related to these architectures in the resource section if you are interested in learning more. In the next few videos, we will also go over some of these in more detail. So see you there.